Let's take a look at the second example of exhaustive search, the problem called knapsack problems. And this also under the optimizations or combinatorial problems involve subset here. What is a knapsack problem? Basically, given n items here with weight, values, and capacity. The goal here actually try to find um, the maximum values in term of for example here the values is in term of money, amount of money within the capacity givens. So we have the weight, we have the values, and we need more values, more item, but within the capacity. This is the problem. In the real world example, maybe consider a transport plane that has to deliver the most valuable set of items to remote location without exceeding the plane capacity. This may be the real problem. In order to solve this problem, actually we need to certain comply with certain capacity here. Okay, let's say here we have the item. We go to the example here. Item, we have 4 items to make it simple. Weight 2, 5, 10, and 5. So item 1 with these 2 weight, maybe 2 kilograms. The value is 20 ringgit. Item 2, 5 kilogram, maybe 30 ringgit. Item 3, 10 kilogram, maybe 50 ringgit. Item 4, 5 kilogram, maybe 10 ringgit. So we need to find that more items but more values within the capacity, because this is the goal of this knapsack problem. To solve this problem knapsack, we have to list the subset here, as we had the example just now. Set 1, which is total equal to 2, total values 20 ringgit. Set 2, 5, 30 ringgit. 3, 10, 50 ringgit. 4, 5, 10 ringgit. And let's say the capacity is 16. So now our aim actually to have more values in term of ringgit here, in term of amount of money, but within 16 capacity, which is actually the weight, the total weight, and regardless how many items. So the more item, actually that will be good for our goal. Okay, now we have set this still within the weight, but now we try to establish another subset, the combination set 1 and 2 here. Okay, 1 and 2 is 7. Okay, still within the capacity. The number of the total amount is 50 ringgit. Okay, and maybe we have a set 1 and 3 here. 1 and 3, so the total is 12, and the amount is 70 ringgit. And we have 1, 4 here. 1, 4 is 7 total, and total values will be 30 ringgit. And we have 2, 3, for example. Try to split this. Through 2, 3 is 15, and the amount is 80 ringgit. And try to 2, 4, item 2 and 4 here, which is the total weight is 10, and the amount is 40 ringgit. Okay, and net is 2, 3, 4 here, and the amount is the weight is 15. In total, ringgit is 60 ringgit. Okay, and net is maybe increase 3 item here. 1, 2, 3. 1, 2, 3. The total weight is 17, and the 17 actually exceeds our limit here, so not feasible here, so we have to do, and so on so forth, until 1 2 3 1 3 4 1 2 4, maybe 1 2 3 4, and make sure that the total weight within 16, the maximum is 16, but we need more values in terms of amount of money. So this is actually the problem with Knapsack, and the solution using Exhaustive Search under the brute force design technique. Okay, in terms of complexity for the Knapsack, actually this problem fall under 2 to the power of n here. These are under our class C, and also this is not efficient, and actually most Fiat's algorithm fall under this. It's good for the small instance, not for the large problems, large input size. And just when only 4 here, then we can produce that the list of possible solution, because as the concept of the style of the brute force, a list of possible solution based on this subset. And finally, the next step is to find which one actually comply with the capacity here, which is 16, but we need more money here, more amount of money here, more values here.